So let's wait for 1 or 2 minutes for others to join, and then after we'll start our lecture. My screen is visible, everyone? Hello? Okay, so listen everyone, in last class I have explained you multiplicative inverse. Okay, based on that I have explained you different example. Now today I will explain you how compute a raised to b mod n. Okay, so now see this particular method that is useful in RSA algorithm. In RSA algorithm, this type of mathematical calculation is there. So similarly, see each and everything, this type of calculation e raised to b mod n, multiplicative inverse, that all mathematical concept that will be explained, that will be using for the lectures. Okay. So today, how to compute the a raised to b mod n. So there are two methods. One is a brute force approach, and another is a square and multiply. Right. So these are the two methods. So now in brute force, all of you know that a how many times the b is multiplied. A is multiplied b times. Okay. So now here, see, I will not explain you how exactly I am getting this complexity. Okay, so this is the topic of that, so I'm not going in detail. So in brute force approach, total multiplication b minus 1 is required, while in a square and multiply method, log b base 2, right? So this is a complexity. So today I will explain you square and multiply method. So this is a fast exponentiation method. Okay, so now see the algorithm. So here a raised to b, the algorithm is a raised to b mod n, right? So now here what you have to do, so whatever the b value is there, first you have to write the binary of that b. Okay, just understand the algorithm everyone, right? So what you have to do, a raised to b mod n, so whatever the b value is there, first you have to perform the binary of that b. Okay, so what you get so some value that you are getting. Now for calculating this, these are the steps that you have to follow. Initially the z that you have to consider 1. Now I equals to k means whatever the beat over here is there, right? So from see from this particular position, one by one you have to take the different beat up towards 0, means up to this you have to see, suppose b is 100, so here some binary value you are getting, right? So one by one all the bits that you have to take, right? And up to this you have to repeat the for loop. Okay, and then at that time what you have to do, z equals to z square mod n, right? And at that time you have to check whatever the beat value, whatever this beat value is there. If the beat value is 1, if it is equal 1, then what you have to do, whatever the value here you are getting z, so what you have to do, z equals to this value whatever you get, multiply with a means this value, okay, mod n. Okay, so in this way you have to follow the steps everyone. Okay, so all of you, have you written this algorithm in last class? Yes or no? See, please communicate with me. So it's very difficult for me to explain you if you are not communicate everyone. Okay. Okay, everyone. So listen, one example I will explain you so you can understand. Okay. So See, here one equation is there, that is 7 raised to 100, 7 raised to 100 more 50. Okay, so now what is the binary of 100? The binary of 100. So see, in this way I am writing. Just wait, everyone. Hello.
Good morning. Am I audible? Okay, Jit, fine. Rick and Harsh. Okay. There was little confusion in lecture, so we start with my lecture. Last time we discussed about principle of mathematical induction and also other proof techniques. One of the proof techniques that we did not discuss is dividing the proof into the cases. So we'll start by that technique today and then again revert back to principle of mathematical induction, PMI. So this is a simple technique, dividing the proof into the cases. Suppose I want to prove a statement for some set of values. So I'll divide those set of values into appropriate number of classes, and for each class I'll prove the statement. Dividing the proof into the cases. So whatever my range is, I'll divide that into appropriate number of classes and I'll prove the statement for each of the class. That is a formal proof technique. You can just compare this with integration by parts. No, while you are integrating, you are dividing into the parts and then integrating each part, and the total answer was the combination of the answer. Similarly, here also, I'll divide the proof into the cases and I'll prove the statement for each case. The thing that is to be taken care here is I should not miss a single value. If I miss even a single value, then my proof is not complete, hence not correct. So dividing the proof into the cases, we'll have appropriate number of cases. Depending upon the problem, there is no fixed rule that how many cases would be there. It depends upon our thought process. We'll divide the total values into the sets, and then for each set, we'll prove the statement. So here is an example. Strings of length 4 contain substrings yy, where y is non-null. Strings of length 4 contain substrings yy where y is non-null. Now I'm applying the proof, dividing the proof into the cases technique. So I don't know how many cases would be there. Every time that will be a question. If I'm not able to apply the technique, proof technique for the entire range, then a rule of thumb could be I divide the proof into the cases. For the entire range, if I'm finding it difficult to prove, then let me try out with the subsets. So here, strings of length 4. So how many cases would be there? I suppose I'm asked to prove this statement using divide the proof into the separate cases proof technique. So how many cases would be there? If I'm unable to think about those cases for this particular example, it could be say number of strings of length 4. How many strings of length 4 are there? How many strings of length 4 are there? Your answer? How many strings of length? See, my sigma equal to 0, 1. Unless specified otherwise, my sigma, that is the input alphabet set, contains two elements, 0 or 1, or maybe A or B, unless specified otherwise. So assuming sigma equal to 0, 1, strings of length 4, how many of them will be there? Waiting for your answer. Strings of length 4, how many of them would be there? Sigma is 0, 1. 16. Yeah, 16. We shall fine, Ricky. It is 16. 2 raised to 4. That is 16. So if I don't know which are all the cases, if I don't know them, then for this particular example, in easiest approach would be I'll divide this into 16 different cases for each of the string. How many elements in sigma star are there? There are 16. When we say sigma star, it means different combinations I get using symbols of sigma. Sigma is my input alphabet set. Here it contains two elements, 0, 1. If I take the English language, then my sigma will contain symbols small a, small b, small c up to small z, capital A, capital B, up to capital Z, then the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and my punctuation symbols. This is my sigma, and from this sigma star, I'll get all the combinations of these characters. English would be a subset of this sigma star because not all combinations are valid English sentences. From sigma having values A to Z small, capital A to capital Z, then digits 0 to 9 and punctuation marks, I can frame any number of sentences. Some of them would be valid, others won't be. So those valid sentences are elements of sigma, and remaining are there in sigma star but not in the language or set English. So that is the meaning of notation sigma star. Sigma means my input alphabet, sigma star all combinations that I can form using those elements of sigma. And sigma star can contain infinite number of elements. Each element in turn can be infinite in length. I can have a string which is infinite in size because from 0 and 1 I can make a very, very large string. And number of elements in sigma star for this example, again there will be infinite. 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, so on and so forth. So let us return to our example. String of length 4. Total possible lengths strings that is equal to 16. And if I don't know what all the cases would be, I'll have 16 separate cases. And for each case, I'll prove that the statement is true. Exhaustive possibility I'm considering. All the possibilities, anyway, I have to consider all the possibilities. But my cases should be such that it covers, the cases should cover all the strings. If I'm not able to properly frame the cases in this particular example, the easiest approach could be I have 16 cases and I take each string separately, and for each string I prove the statement. So nothing remains. All the string in sigma star of length 4 we have considered. And if we can prove each of the cases, then the statement is true for the entire range. So what does that mean? Strings of length 4 contain substrings yy. So within that string, I must have a pattern repeated. Substring yy where y is non-null. So what happens? Instead of 16 cases, you take any string. I can show yy. We have to show for every string yy. So if we take 16 separate cases, for each one we'll show that there is a repeated pattern. But however, this is not required to have 16 cases. In fact, instead of 16 cases, we can work out this example with only 2 cases. And here are the cases. X contains 2 consecutive zeros or 2 consecutive ones. X contains 2 consecutive zeros or 2 consecutive ones. And case number 2, any symbol that follows a 0 is 1 and vice versa in X. These are my cases, only 2 cases that will cover all the 16 strings. Case number 1, X contains 2 consecutive zeros or 2 consecutive ones. Case number 1. In the second case is any symbol in X, for any symbol 0 in X is followed by 1 and vice versa. So something like X is starting with 0, next will be 1, then will be 0, then will be 1. If it is starting with 1, next symbol is 0, next is 1, next is 0. So these are the possibilities in case 2, whereas here 2 consecutive zeros are present. 2 consecutive zeros or 2 consecutive ones are present. These 2 cases will cover all the 16 strings. So I don't require to have 16 cases, only these 2 cases are sufficient. And in both the cases I will prove the statement. So here there are 2 consecutive zeros or 2 ones. And what I require in X, a repeated pattern. It contains substring yy. So y and y gets repeated, so it is said yy. So if there are 2 consecutive zeros in X, then my first y is 0 and second y is 0. So that yy I am looking for, that is 0 0. Y that I am looking for is 0. Y that is 0. Second y is second 0. There are, under this particular case, it is known that X contains 2 zeros, 2 consecutive zeros or 2 consecutive ones. And I am looking for repetition of the pattern. So if there are 2 consecutive zeros, then my first 0 is first y, second 0 is second y. Similarly, if there are 2 consecutive ones, my first y is 1, my second y is the next one. So under this case, irrespective of remaining symbols, I am getting the pattern repeated 0 0 or 1 1. My y is either 0 or 1. Remaining symbols could be anything, that does not matter. I require a substring having a repeated pattern. So that substring is either 0 0 or 1 1. So the repeated pattern is respectively 0 or 1. So under this case, I have shown that X contains the X in string, it contains the pattern yy. The substring in X contains the pattern yy that we have shown under this case. In only 2 cases, only 2 strings. That is case number 2. That is either 0 1 0 1, 0 is followed by 1, or 1 is followed by 0. Any symbol that follows 0 is 1 and vice versa. So after 0 1, after 1 that is 0, after 0 that is 1. That is my first string. And the second case is 1, then 0, then 1 0. In this case, the repeated pattern, it's obviously visible, is either 0 1 in the first case, 0 1 0 1. So the repeated pattern is my first y is 0 1, my next y is 0 1. Here we are taking the entire string. In the previous example, in the previous case, what we have taken? Substring 0 0 or 1 1. So there are 2 more symbols, but it doesn't matter because we require only one yy. In this case, my substring, I'm taking the entire string. X is 0 1 0 1, length 4. I'm taking the entire string. And my repeated pattern here is 0 1. That is the repeated pattern. My first y is 0 1, second y is 0 1. Similarly, in the next case, my first y is 1 0, second y is 1 0. So in both the cases, we could find a pattern yy in the substring of X. So sigma case 1, case 2, my proof is over. The statement is true for every string in sigma star having length 4 when sigma is 0, 1. So that completes the proof. Dividing the proof into the cases, that is how it works. Is that clear? Is that clear to all? Okay. Fine. Harsh, Keval, Abhi, another Harsh. Okay. Rikin, good. So now we again return to our principle of mathematical induction. This proof technique we did not discuss in the last lecture. That was the remaining one. Now we return to our principle of mathematical induction. So when we use principle of mathematical induction, the statement P has to be in terms of some integer n. We require integer n. And in order to prove the statement for the entire range of n, starting with the seed value n0, we just need to prove it for the initial value or the seed value, and then we need to prove for P of k plus 1, k greater than or equal to n0. We need to prove for k plus 1, assuming that it is true for n equal to k. So if pk, then P of k plus 1 for k greater than or equal to n0. This we had worked out. Let us go to the next example. For all n greater than or equal to 1, n cube plus 2n is a multiple of 3. Example number 2, I had shared these notes. I will repeat this. It's part of the note that has been shared. Prove that for all n greater than or equal to 1, n cube plus 2n is a multiple of 3. This is example number 2 for principle of mathematical induction. So whenever we want to prove a statement using PMI, we must look for integer n. Incidentally, in this example, n is present. The example itself, it is in terms of n. So first step, to write the statement Pn, write the statement P in terms of n. Already it is there. N cube plus 2n is a multiple of 3. This is my statement Pn. Let P of n be the statement n cube plus 2n is a multiple of 3. And also we should specify the range of n, already given in the statement. So say we have to prove the statement for n greater than or equal to 1. The first step using PMI is to write the statement. Statement is written. We have to specify the range that we have done. Now, there are 3 components as seen in the last example. There is basis, hypothesis, and induction statement. We prove for the initial value, that is called basis. If P of k, then P of k plus 1. So that if P of k, that assumption, that is called hypothesis. And then P of k plus 1, that is induction statement. So we need to prove basis. We need to prove the induction statement. Basis, seed value, initial value, we know n starts with 1. So n0 equal to 1, the initial value is 1. And P of 1 is true. That is my basis. P of 1 is true. And that P of 1 is substituting n equal to 1 in the statement. So 1 cube plus 2 into 1. So 1 plus 2, that is equal to 3. And 3 is a multiple of 3. So that completes proof also. 3 is indeed a multiple of 3. Basis part is over. The second part in PMI, that is hypothesis, assumption. And in the assumption, we start by specifying the range of k. In range of k, it is same as range of n. So this is my hypothesis. P of k greater than or equal to 1. So that is range of k. And P of k is assumed to be true. So we'll put in the original statement n equal to k. That is my assumption. That is k cube plus 2k is a multiple of 3. My statement is what? n cube plus 2n. So we put n equal to k. So that is k cube plus 2k is a multiple of 3. That becomes my hypothesis. K cube plus 2k is a multiple of 3 for k greater than equal to 1. That is my hypothesis. This is assumption. Comes the induction statement. That is n equal to k plus 1. We have to prove the statement. For n equal to k plus 1, we have to prove the statement. We have to prove p of k plus 1, assuming that p of k is true. So here we'll put k plus 1. So that is k plus 1 cube plus twice k plus 1 that we need to prove. That is a multiple of 3 that we need to prove. K plus 1 cube plus twice k plus 1 is a multiple of 3 is to be proved in simple expansion. A cube plus b cube. This is a cube, that is k cube, plus b is 1, that is 1. A cube plus b cube plus thrice a square b plus thrice ab square. So that is 3k plus 2k plus 2. It's a simple expansion. And out of that we keep aside k cube plus 2k. We keep aside k cube plus 2k because as per the hypothesis, k cube plus 2k is a multiple of 3. We don't require to prove anything. So from these expanded terms, we keep aside k cube plus 2k, and then we have remaining terms. That is 3k square plus 3k plus 3. So that is 3 into within parenthesis k square plus k plus 1. So k cube plus 2k we know is a multiple of 3 using hypothesis, that we know. And the second term, the expression, that is multiplied by 3. Therefore, the entire expression is a multiple of 3. Therefore, p of k plus 1 is true. So that completes example number 2. The entire expression, the first part is a multiple of 3 because of hypothesis, and second part it is 3 multiplied by some term. So the entire expression is a multiple of 3, which we needed to prove. So that completes proof for p of k plus 1. For n equal to k plus 1, the expression that we get is a multiple of 3. Completes the proof. Is that fine, students? Is that okay? Rikin, Shail, Kaushal, okay, Utsav, Yash, Abhi, Love, fine, nice. So now we go to the third example. That L be a language in sigma star for some alphabet sigma, and consider the statement: if L square is a subset of L, then L of plus is a subset of L. L be a language in sigma star for some alphabet sigma. Consider the statement: if L square is a subset of L, then L plus is a subset of L. Now for this example, in order to apply PMI, what is the difficulty here? Unlike earlier two examples, we want to apply PMI. Here, unlike two other examples, the problem here is, yes, Harsh? No, we don't have any integer present in the statement. There is no integer. We require, in order to use PMI, we require integer n missing in the statement. So it is explicitly missing. We will explicitly introduce n. Somehow we'll introduce n in the statement. What could be, how can we introduce n? Is it possible to introduce n in this statement? Can we introduce explicitly n in this statement? Try to think. Bhavik Ardeshna is saying size of L. Can you further elaborate, Bhavik? Can you unmute and answer, Bhavik?
Like we assume the length of L means your language, which is in sigma star for all alphabets, like assumption only.
Okay. Okay, fine, Bhavik. Jit, can you explain your answer? Jit? Can you unmute and explain your answer? Jit?
Sir, for null character, first we'll prove L power 0, and then for L up to 1 to n, and then we'll exclude that null character. So we'll get L plus.
in the statement explicitly, where we'll put n?
uh, L raised to 1, L square, then L cube.
So we'll put, instead of L plus, we'll put ln raised to n.
Yes.
Instead of L plus, we'll put L raised to. Fine, you can unmute. You can mute yourself. So n is missing. Bhavik, actually we cannot change the statement, because if you take different combinations, I mean, we can introduce integer n without changing the meaning of the statement. We cannot change the statement. In the meaning of L plus, in computer science, when we say L plus operator applied, it means it is one or more occurrence of a particular pattern. Even in Unix, Linux, you must have studied, no? Plus we apply. It means one or more occurrence of a pattern. Shell programming, you must have written use these regular expressions. So that means one or more occurrence. When we say star, then it is zero or more occurrence. Therefore, here we will not even write zero. We cannot write zero actually. Though writing zero, we are proving a superset. Therefore, our statement or the argument won't be wrong. But ideally, this means L to the power n, where n is greater than or equal to 1. So that is how we explicitly introduce n in the statement. L is a sigma, let L be a subset of sigma star as it is. And if L square is a subset of L, then L raised to n. And L raised to n is a subset of L. And this we will prove for n greater than or equal to 1. Ideally, it should be 1. Just for a specific reason, we have taken 2. Ideally, it should be 1, because that is meaning of L to the power plus, one or more occurrence of a pattern. So we'll prove this Pn for n greater than or equal to 1. Now, if you put n equal to 1, I mean the seed value, the starting value is 1, then what we need to prove? L is a subset of L. So nothing is required to be proved. L is indeed a subset of L when n equal to 1. That becomes my base case as per this. However, just to illustrate that, the starting value could be other than 0 or 1. For that particular reason, we say we are proving for n greater than or equal to 2. Because for L equal to 1, L is a subset of L, nothing is required to be proved. Starting value could be anything. To emphasize this fact, we here take liberty to say n greater than or equal to 2. As per actual statement, it should have been n greater than or equal to 1. But then we are not losing anything. We are not losing any case. Therefore, we say n greater than or equal to 2. You can safely say n greater than or equal to 1, no problem. Fine. So if even for L n greater than 2, we don't need to prove anything in the case of the seed value, the base case. Because there still it becomes L square is a subset of L that we need to prove, but then that is given. If L square is a subset of L, then L to the power n is a subset of L that we have to prove. And when n equal to 2, the statement becomes if L square is a subset of L, then L square is a subset of L. So if L square is a subset of L, that is given. So nothing much to be proved. When we say n equal to 1 or 2, that is given. L square is a subset of L, that is given. So that is proof for the basis, already given. Hypothesis, we talk in terms of K. We specify the range of K. So K is greater than or equal to 2. Range of K is same as range of n, because this is for, when we say K, it is any value of n. For any value of n, if the statement P of K is true, then P of K plus 1 is true. So the range of K is same as range of n. K greater than or equal to 2, and P of K is assumed to be true. So if L square is a subset of L, then L to the power K is a subset of L. This is my hypothesis. In this statement, I substitute n equal to K. So if L square is a subset of L, then L to the power K is a subset of L. That is hypothesis. That is assumed to be true. Similarly, in the induction statement, we substitute n equal to K plus 1. So if L square is a subset of L, then L to the power K plus 1 is a subset of L. This is my induction statement. Always we need to prove basis and induction statement. Hypothesis is my assumption, assumed to be true. Basis we have proved, because if L square is a subset of L, then L square is a subset of L, nothing to be proved. Or if had we taken n equal to 1, n greater than or equal to 1, then if L square is a subset of L, then L is a subset of L. L is always a subset of L. Fine. So L square is a subset of L. Whenever we go to the proof for the induction statement, most of the time we look at the use of hypothesis. Using hypothesis in the proof will help us in proving the induction statement easily. That will simplify the task of proving the induction statement. Somehow, if we can use the hypothesis, though it is not compulsory to use the hypothesis, only requirement is if pk is true, then p of k plus 1 is true. So p of k plus 1 has to be true. Anyway, we can prove. In multiple ways we can prove if we, but easiest thing will be to use hypothesis. So hypothesis that is given to us is L to the power k is a subset of L. L square is a subset of L, that is given. In that case, L to the power k is a subset of L. So that is from the hypothesis. And now we use the simple property of language concatenation. Applying L left hand side to the left hand side and to the right hand side in this subsethood relation. So LK language dot, that is concatenation dot is that LK dot L is a subset of L dot L, and that is the property of language concatenation. This is true because of the basic property of language concatenation. So we get L to the power k plus 1 to be a subset of L square. LK dot L is L to the power k plus 1 as per the definition of language concatenation. You must have already studied in the first chapter other part, or you will be studying that soon. L dot L, that is L square. So what we get? L to the power k plus 1 is a subset of L square. But then L square is a subset of L, that is given. That is given. The basis also given also. So L to the power k plus 1 is subset of L square. In turn, L square is a subset of L. Therefore, L to the power k plus 1 is a subset of L, applying transitivity on subsethood. L to the power k plus 1 is subset of L square. In turn, L square is a subset of L. Therefore, L to the power k plus 1 is a subset of L, applying transitivity on subsethood. That is my proof. That is my proof. Is this fine? Pavik, Chit and other students, is this fine? The proof is fine? Okay, Rikin? Yash, Jit, Janil, fine. Okay. Aksh. Next let's see. Yeah, let us prove this statement. Consider the following fragment of a Pascal program. Consider this of a Pascal program. Read Xn, just look at the code. Read Xn. So Xn in our input. Pascal was the first structured programming language. So prior to C, Pascal was very popular, and conceptually it is very much similar to C. So consider the following fragment of a Pascal. Assume that all variables are of type integer. So read Xn, that is my Xn n are taken as an input. Y is equal to 1 initially, for I equal to 1 to n, y equal to y into x, and right line, that is our printf y. Consider the following fragment of a Pascal code. Assume that all variables are of type integer. Here is the code in Pascal, and finally we write the value of y. And here is a statement. You want to make a statement about ultimate value of y printed out of the program. After the loop is over, we want to print the value of y. Can you just see what will be y? Channel 1. Okay. Assuming that initial value of variable x, capital X, is small x, what will be this? X raised to n. Correct. That is fine. X, small x to the power n. So this initial value of y is 1, and we are multiplying y with the value of x. So if the value of capital X is x, then that is 1 into x, and this is loop 1 to n. So every time in a loop we multiply the initial value by small x. So this is executed n number of times. So that is small x to the power n. That is the final value of y, and that we print after the loop. That is write ln y. So we want to make a statement about ultimate value of y printed out of the program, out of the loop. What is the value that is getting printed? And here is my statement Pn. We make a statement and we'll state about the ultimate value of y that is printed when we come out of this this loop. If the value of x is x, then the value of y, the initial value of x is x, then the value of y after loop has been executed n times is small x to the power n, or any n greater than equal to 0. This is my statement Pn. We are making a statement regarding the value of y, and initial value of variable x is small x. So that is after the loop has been executed n number of times, then this will be small x multiplied by, in every iteration we multiply x by x, so we have x to the power n after the loop has been executed n number of times. That is value of y, and we wish to prove this for any n greater than equal to 0. Is this fine? Range of n, that is fine? Is the range of n correct? Is the range of n is correct? Your answer? Is it 0 or should it have been 1? N greater than equal to 1. Is Janil correct? Rikin and Janil are correct? Are Rikin Janil correct? Is the statement true when n is less than 1 or n equal to 0? Is the statement true? Even it is true if n equal to 0, no? Because initial value of y equal to 1 and x, small x to the power 0. That is correct. Small x to the power 0, that is 1. So even for n equal to 0, the statement is correct. Loop is not getting at all executed. Value of y equal to 1. So that is small x to the power 0. 0 number of times the loop is executed. So small x, initial value of x is small x. Number of times the loop gets executed is 0. So small x to the power 0, that is 1. And that is value of y equal to 1. We have initialized y to 1. So yeah, correct. General, fine. N greater than equal to 0. Fine. So we need to prove the statement for n greater than equal to 0. Please understand that in the last example, we need to prove Pn for n greater than equal to 1 as per the formal definition. It's better to prove for n greater than equal to 1. Just for the illustration, we have taken n equal to 2. Ideally, it should be 1 because that is the meaning of plus. Similarly, here we'll take n greater than equal to 0 and not 1. N greater than equal to 0 and not 1 because the statement is true even when n equal to 0. So initial value of n, that is 0. We have written statement Pn. It is in terms of n. Now it is there. And we have specified range of n. So that part is over. Now 3 components: basis, hypothesis, and induction statement. And my basis is P of 0 is true. The value of x is x. And after 0 iteration of the loop, the resulting value of y is x raised to 0. Already we have discussed. Loop is not getting executed at all. And initial value of y equal to 1. Therefore, the printed value is x, small x to the power 0. That is 1. So the statement is correct. This is indeed true because initial value of y is 1. And the loop is not at all iterated. The statement is correct. Y equal to 1. 0 iteration of the loop. That is, loop is not iterated. X to the power 0 is 1. So y is correctly printed. Y is correctly printed. Next is the hypothesis. Specify the range of k, same as range of n. Therefore, k greater than equal to 0. And after the k iteration of the loop, assuming that the initial value of x is x, the printed value of y is small x to the power k. The same statement. The same statement as Pn. Only thing we replace n with k. If the value of x is x, then the value of y after the loop has been executed k number of times is small x to the power k. Already we have specified the range. So k greater than or equal to 0, and after the k iterations of the loop, assuming initial value of x is x, the value of y is small x to the power k. And in the induction statement, that becomes x to the power k plus 1. That is k plus 1 iteration of the loop. The value of y is x to the power k plus 1. The initial value of x is x, then after k plus 1 iteration of the loop, the value of y is small x to the power k plus 1. Small 1 or 2 lines not visible to you. Last 1 or 2 lines not visible to you. So if the initial value of x is x, then after k plus 1 iteration of the loop, the resulting value of y is small x to the power k plus 1. Almost same as hypothesis. We don't specify range of k. Instead of k, that becomes k plus 1 iteration of the loop. Resulting value of y is small x to the power k plus 1. That we need to prove. How do we prove this? How do we prove this? How do we prove the induction statement? Think about proving the induction statement. In the induction statement, see how can we use hypothesis. Try to use hypothesis in proving the induction statement. If anyone gets the argument, can unmute and answer. If someone wants to answer this, can unmute and answer. Anyone wants to answer this? How should we argue in the induction statement? Anyone wants to answer this? See, by K, yeah, yes, Jit, exactly. Can you just unmute and speak this, Jit? Jit?
Sir, by k plus 1 iterations, we'll get value x power k plus 1. So we'll divide it into x raised to k multiplied by x. So we just hypothesis.
Okay,
Yes,
fine, that's fine. Okay, mute yourself. The way we present is slightly different. Fine, the concept remains the same, of course. By k iterations of the loop, assuming initial value of x is x, the value of y, the resulting value of y is x to the small x to the power k. That is hypothesis. What is that? K iteration of the loop, initial value of x is x. After execution this loop k number of times, the value of y is small x to the power k. That is as per the hypothesis. We are not stating anything. We just take the hypothesis. Now there is one more iteration. That is my k plus first iteration, wherein the previous value of y, there is one more iteration. That is my k plus first iteration, wherein the previous value of y gets multiplied by the current value of x. So in k iterations, the previous value of y was small x to the power k, and that gets multiplied by x in the k plus first iteration. That gives me x to the power k plus 1, and that is my final answer. After k plus 1 iteration, value of y is small x to the power k plus 1. That is what, after k iterations, the resultant value of y is x to the power k. That is from the hypothesis. After k iterations have been performed, the loop will be executed for one more number of iteration, that is n equal to k plus 1. And as per the program, the new value of y is the previous value of y multiplied by value of x. That is x to the power k multiplied by x, which is x to the power k plus 1. So this is my formal argument. That is y equal to the power k plus 1 completes the proof. That completes the proof. Is that fine to everyone? So this is more formal than what Jit said earlier. Logic remains the same, but our argument is more formal because we don't need to argue that after k iteration it is x to the power k. Only for the k plus first iteration we have to make a statement. So that is the previous value as per the program, previous value multiplied by x. That gives me x to the power k plus 1, and that is my formal proof. That completes my formal proof. Is it fine? Rikin, Harsh, Shail, okay. Abhi, Jainil, okay. Okay. Now we move to the next example. Given a language L equal to A3, A7, or maybe last time we had discussed this proof using minimal counterexample principle. One of the examples that we worked out, there was a power failure in the previous lecture, so the lecture got immediately suspended. By minimal counterexample principle we had worked, we discussed about this. Now we know PMI. Let's once more repeat this. We did not discuss this second example. It's very simple, but because now we have worked out sufficient examples on PMI, once again, just to brush up the things, we can talk about the second example of proof by minimal counterexample principle. For every positive integer n, prove that n square minus 3n is even using minimal counterexample principle. N square minus 3n is even using minimal counterexample principle. So now we know PMI in detail. This minimal counterexample principle, it is considered to be a disguised form of PMI. That's, I think, that statement we had made. Yeah. Proof using minimal counterexample principle, it is considered to be a disguised form of principle of mathematical induction. Why is it said so? Because like PMI, we prove base case. Exactly same. The statement is there. We specify the range and we prove the base case. 100% same. Principle of minimal counterexample principle and principle of mathematical induction. We prove the base case. So here also, the statement is true for n greater than or equal to 1. For every positive integer n, prove that this is even using minimal counterexample principle. This is true for n greater than or equal to 1. My base case is P1. P1 is 1 square minus 3, that is minus 2, that is even. That is even. So we have proved the basis of PMI. Here it is called the base case. The first thing is over. Now what we do in the case of PMI, we assume that for any value of n equal to k, the statement is true. So we specify k greater than or equal to some range. Range of k is same as range of n. So for any value of n equal to k, the statement is assumed to be true. And then we prove p of k plus 1. Whereas here, we assume that for n equal to k, the statement is false. Here is the difference. In fact, not only for n equal to k, here for the set of values, the statement is assumed to be false. It is not true that the statement is true for every value of n specified in the range. That is our assumption. And among these values which make the statement false, the minimal being n equal to k. So we assume that for n equal to k, k is the smallest value which makes the statement false. That is the assumption, whereas in the case of PMI, the assumption is for any value n equal to k, the statement is true. And then we prove n equal to k plus 1 in the conventional way in the case of PMI. Of course, we use hypothesis to make the process simpler. Whereas here we use what is called proof by contradiction actually. We make an assumption and then contradict our own assumption. That is the philosophy behind proof by minimal counterexample principle. Actually, it is said to be a disguised form of PMI, but it is not only disguised form of PMI, it is also a combination of PMI and proof by contradiction. That is more specific statement. It is considered to be a disguised form of PMI, but if we make a statement that it is PMI plus proof by contradiction, that is even more specific statement. So that is my hypothesis part of PMI, that is assumption that the statement is not true for every value. Now let's assume that Pn is not true for all values of n. The smallest value for which Pn is false is k. And we have already proved for the base case. Our statement was, the statement is required to be proved for n greater than or equal to 1. We always prove the base case. So for the base case, the statement is true. So if it is false for some value, it cannot be this base value because already we have proved it. So k has to be at least 2. As P1 is already proved to be true, k is at least 2. For k, the statement is assumed to be false, and k is at least 2 because P1 is already proved to be true. So putting this n equal to k, n square minus 3n, that becomes k square minus 3k. That is not even. The statement is that it is even. So for n equal to k, the statement is false. So it is not even. It means it is odd. When we say it is odd, it means I can write that equal to 2i plus 1 for some I belonging to z. For n equal to k, the statement is false. Statement is that n square minus 3n is even. So for n equal to k, that becomes k square minus 3k. That is not even. It means it is odd. And when we say it is odd, it means we can write k square minus 3k equal to 2i plus 1 for some integer I, for I belonging to z. So up to this point, fine. Now, k is the smallest value for which Pn is false. Therefore, P of k minus 1 has to be true. Here we are now we search for the contradiction. We assume the statement is not true for every value. Smallest value for which the statement is false is k. It means for k minus 1, the statement is true. So as k is smallest value for which the Pn is false, for P of k minus 1 has to be true. And we write this expression because ultimately we are looking for the contradiction. Assumption part, k square minus 3k, that is not even. That expression we have got. Now k minus 1, it is true. For k, it is false. And we'll get another expression. And between these expressions, we always look for the contradiction. We need contradiction. So P of k minus 1 is true. So again, n equal to k minus 1 in my original expression, that becomes k minus 1 square minus 3 into k minus 1. That is even because P of k minus 1 is true. So k minus 1 square minus 3 of k minus 1 is even. The original statement. N square minus 3n. We are putting n equal to k minus 1. We are substituting n equal to k minus 1. That is even. So that is k minus 1 square minus 3 into k minus 1. That is even. That is even. So when we say even, it is means k minus 1 square minus 3 into k minus 1 is equal to 2j. When something is odd, for example, n equal to k, that is k square minus 3k, that is 2i plus 1, where I belongs to z. Here, k minus 1 square minus 3 of k minus 1, that is equal to 2j, where j belongs to z. Now we expand this k minus 1 square minus 3 of k minus 1. So k square plus 1 minus 2k minus 3k plus 3, that is equal to 2j. We are expanding, we are just expanding. And then we are eyeing the hypothesis, similar to hypothesis, n equal to k. We are eyeing k square minus 3k. So we are out of these expressions, we keep aside k square minus 3k. And the remaining part, that is minus 2k plus 4, that is equal to 2j. So k square minus 3k, taking 2 common, we have 2 minus k, that is equal to 2j. So k square minus 3k, that is equal to 2j minus twice 2 minus k. That is equal to and then expanding that further, again not visible, that is k square minus 3k, that is equal to 2. If we take common 2, k square minus 3k, what if we take common 2, then we'll get j minus 2 plus k. So what we have got, k square minus 3k is 2 multiplied by, within parenthesis, j minus 2 plus k. So we are getting that to be a multiple of 2, which means we are getting k square minus 3k to be a even number. That is, k square minus 3k is 2 into L, where L equal to j minus 2 plus k. So we are getting k square minus 3k is equal to 2 into L, where L belongs to Z. It means we are getting k square minus 3k to be an even number, which contradicts the assumption that k square minus 3k is 2i plus 1. It is an odd number. We have proved that we are getting k square minus 3k to be an even number, and that is the contradiction we were looking for. Therefore, the assumption that the statement is true for some set of values, that is false. In fact, no such k exists. Therefore, the statement is true for the entire range n greater than equal to 1. That is example 2 of principle of minimal counterexample, or minimal counterexample principle, proved by minimal counterexample principle. Is that fine, friends? Any doubt in this? Rikin, Jeet, Harsh, Tumars, Keval, Love, Kaushal, fine. Okay. So, yes, Harsh Patel, fine. The next lecture will continue from this. Next lecture will continue from this point. We'll take more example of PFI tomorrow. Thank you. We stop here.